much for the welcome and for these wonderful presentations. This is a paper that I recently thought about making. That's actually a continuation of my PhD, of my recently finished PhD thesis. And its title is The Effect of the Adjacent Tooth and Rim Elasticity on Fatigue Behavior in Thin Rim Spur Gears. So basically what I want to start with is the layout of the presentation. So first we will talk about introduction part about what exactly is the problem with thin rim gears and gears in general, about bending fatigue, what happens, why are they breaking, what can be done. After that, something about materials and methods. So we specifically used finite element method and fatigue modeling methods to investigate how what is the estimated bending fatigue life of some gears within rims. We'll talk about a bit what are the gears with thin rims and how are they different from solid or full body gears. Before the conclusions, we'll talk about results and discussion. We'll compare some estimated fatigue cycles according to the existing standards, which are a bit conservative according to the method proposed here, or actually the method was proposed in my PhD, but actually used here or applied here to thin rim gears. And afterwards, we'll conclude the presentation. I estimate about 7 or 8 minutes top, so I will not take up too much of time. So first, something about gears. Basically, we all know that they are one of the most commonly used power transmission elements. You can find them almost everywhere, both metal gears and plastic polymer gears. They're used in industry, and first specifically the thin rim gears, not the full gears, but the thin rimmed ones, are used in the industry that favors lightweight components, such as aerospace industries, for example, helicopters or something like that. Maybe drones. These days they're very famous, where every kilogram or every gram, more specifically, is important. So we try to reduce the weight as much as possible while maintaining the structural integrity of a gear. The main problem is that the existing standards, when they calculate, such as ISO standard, I believe it's 6336. It does not account for the elasticity of the thin rim or for the adjacent tooth effect. Now, these terms might be a bit, might be unfamiliar with, but I will explain what they are in the following image. So we can see on this image, the bottom gear is the normal gear, spur gear, the solid gear, or the full body gear, and the top one is the thin rim gear. Why thin rim? Because you have this part right here, which is actually the thin rim. The mass has been reduced from this part, and this part to reduce the weight of the gear, making it more favorable for using in a lightweight component industries such as aerospace industries. So if you observe the tooth root fillet, this one here, denoted with the red color or bright pink color, this is where problems occur most of the time. Why? Due to the bending fatigue, because this tooth, as the torque is being transmitted from the drive to the driven gear, we have some sort of bending moment that acts around this tooth, and we have high stresses, which are mostly tensile. And then with time, since the gears are rotating, we have a cyclic behavior. Material fatigue will occur in the tooth root, and we will have some problems. Now, what we did is that we investigated how the elasticity of this rim affects this bending fatigue in the tooth root, and also how does the adjacent tooth affect this behavior. What is the adjacent tooth effect? Well, if we take, for example, the rotation of the gear in this direction, as shown here, the observed tooth root fillet, once it exits the contact, the next tooth or the adjacent tooth, which is shown here, comes into contact with its gear, with corresponding gear tooth on the other side. And then in this region, you have compressive stresses, so negative stresses. Tensile stresses are positive and compressive are negative. So we have a compressive zone which changes the cycle that this tooth root fillet experiences. We will show this on the next image. If you can take a look at the right side. On the vertical axis, we have this bending stress that occurs in the tooth root fillet. Plus size, we have tensile stresses. Negative size, we have compressive stresses. So what does the existing standards do? If we take a look at the blue, only the blue line, this is the calculation according to the existing standards. They do not see anything below the 0 point. So there's no compressive stresses, as you can see here. The bending stress cycle is purely tensile, so from 0 to some value. However, this value is often multiplied by some factors, and then you have a value that's overestimated. Actually, it's conservative, it's much safer, but it's overestimated. The actual values the actual cycle of the tooth root can be seen by this orange line that transfers into a purple line and then again into an orange line. This is actually a much more realistic cycle, and we can obtain this cycle by using a finite element method. This cycle accounts that there is some elasticity in the tooth in the thin rim, which changes the contact behavior between these gear pairs. That's the first thing. And the second, it also accounts for the adjacent tooth effect. As you can see, this region right here and this region right here, the orange shaded regions, are due to the adjacent tooth effect and rim elasticity. So what happens? You have a maximum tensile value around the peak of the purple line, and then you also have the minimum compressive value around here. So the cycle, it's from here and here. It's not according to the standard from 0 to the maximum tensile value. So some estimated bending fatigue lives will also be changed due to the changes in the cycle. Okay, now let's talk about some materials and methods used in this investigation. So first of all, the model is based on finite element method. Perhaps some of you have heard about it. It's really very famous in the past 10, 20, maybe even 30 years. It's sort of a numerical simulation that's used to obtain stresses and strains at some components. For example, we can see the model used in this investigation. We can see the driving gear, Z1, and the driven gear, the test gear, because it has a thin rim, as you can see right here, it's Z2. We connected these two inner hubs of the gear to the reference point within, I believe this software we used was Abacus. It is a software used for numerical simulations. Actually, it operates based on the finite element method. And we allow the rotations of this gear, the test gear, in this direction. We measured the rotation with the angle theta. And we also used, we applied torque on the driven gear, and it actually rotates in this direction. And this is our observed tooth root fillet. We chose it right at the middle of this thin rim because we wanted to investigate, we want to take the point that has the maximum elasticity effect, and that will be actually this point in the middle. So apart from the finite element method, we use that one to obtain linear elastic stresses and strains, but we also need some fatigue methods to estimate some bending fatigue cycles, life cycles in the observed tooth root fillet. So this model was based on a strain life method. Other famous method is also stress life, but we chose the strain life method due to some other reasons. They're both actually quite accurate, but strain life method can also be used to evaluate bending fatigue lives both in low cycle fatigue and in high cycle fatigue. Whereas the stress life SN method is actually better for high cycle, but not so much for low cycle fatigue. So this is the example of an Baskin-Coffin-Manson relation based on the strain life method, where we can actually have some parameters such as fatigue strength coefficient, fatigue strength exponent, I believe, fatigue ductility coefficient, and fatigue ductility exponent. And this NF, or actually 2NF, is the number of cycles that the component will last. E is the modulus elasticity for the steel, and sigma M is actually the mean stress that is present in a cycle. The third most important method, apart from the finite element method and the strain life method that we used, is the hardness method. That's actually proven useful in the past. Basically, what it does, it finds all of these parameters shown in the previous equation based on the hardness of the material. So we can use hardness testers such as Rockwell hardness, Vickers hardness. In this case, they actually require Brinell hardness. And once we have that value from the tooth root of the fillet, we can actually use it to estimate these values sigma F, epsilon F, B, and C that are used in the top equation. Once we have those parameters, we can actually find the 2NF, or just simply NF, which is actually number of cycles or number of reversals until fatigue failure. Okay, now the most important part, actually the results and some discussion. Just a quick slide, but maybe the most important one. So what we're seeing here is actually on the vertical axis, we can see the torque that we applied to the gears. So we started from 100 Newton meters all the way to 300 with an interval of 50 Newton meters. And down we can see the number of cycles until failure that we estimated according to our models. First, once again, let's take a look at the blue dashed line, which is the standard, the existing standard for gear calculations that actually assumes that all teeth are ideally rigid. They do not deform. There is no elasticity of the rim. So we get some results that are a bit conservative. For example, for 300 Newton meters, we get a bit more than 100 cycles right here. And these results, we say they're conservative because they're on the safe side, on the safety side. Because if we estimate that something will break at only 100 cycles, whereas it may last up to a couple of thousand cycles, we are on the safe side. However, This is not really maybe desirable today, because we want to get the most accurate results, not necessarily the most conservative results. Because if we get the conservative results, we will have to improve the material, we will have to add some mass so that we can increase the load capacity of the gear, which of course is more expensive, and we're not actually achieving the mass reduction that we wanted to achieve with the thin rim gears. After that, let's take a look at the purple line, which is actually a more realistic cycle, but it is a cycle that does not account for the compressive portion. If we remember at the second slide, we saw the orange shaded areas. Those were the compressive regions due to the thin rim and rim elasticity, which have to be accounted for due to the adjacent tooth effect to get the most realistic approximation. And these results are actually not conservative at all. They tend to overestimate the actual number of cycles. These arrows, as we can see right here, there's no damage after 10 to the 9 cycles, which is a huge amount of cycles. This right here, you can see according to the FEM, according to the finite element method, but there's no compressive stresses, only tensile stresses. The most realistic cycle is actually the one shown with the orange, where we use the finite element method, the numerical method with fatigue life estimation methods. And we also take into account the compressive stresses that actually occurred due to the adjacent tooth effect and the elasticity of the rim. So these are the most realistic results, and we can actually see that there are some differences for higher torques, but these differences tend to be smaller and smaller as we approach the lower torques and the high cycle fatigue. So this line is the most accurate one, and this line should be, of course, used when you tend to estimate the bending fatigue life of thin rim gears. Of course, we have to plot some sort of safety, safety lines on the left and right sides to ensure that we are statistically within a statistically relevant area. But this line is the most realistic. So we can see that there are some quite noticeable differences between the standards, the most accurate results, and the results from the purple line where no compressive stress cycle is taken into account. Why was this purple line shown? Because when researchers tend to use finite element method to investigate such matters, they often plot absolute values of maximal principal stresses. So they do not look below 0 because they often neglect that part. That may be true and may be acceptable in solid gears, but in thin rim gears, you have to account for the compressive stresses, because these stresses actually modify both the mean stress and the maximum stress that occurs in a single cycle. Okay, so that brings us to the conclusion. So basically what we did in this paper is that we use finite element method and fatigue model methods to investigate, or better to say, maybe to estimate fatigue lives of thin rim gears. What we found out is that the standard, as I mentioned before, ISO standard 6336, which is in charge for both thin rim gears and full gears and solid gears, they tend to underestimate actual results, which might be okay, but that might lead to overdimensional components. So you might use a gear that is maybe 15 or 20 millimeters thick, whereas you maybe only need a 10 millimeter thick gear, or those dimensions can be much higher. Now, when you multiply that with the number of gears in the actual machine, you are not really reducing to weight as much as you would like to. So these results tend to be underestimated, but they might result in overdimensional components. And lastly, not accounting for the compressive stresses due to the adjacent tooth effect and rim elasticity significantly overestimates the results, as we saw with the purple line, which shows that most of the applied torques, the gear will actually last more than 10 to the 9 cycles, which is not really true. And with that, I would like to finish my presentation. Thank you all for listening. If you have any questions, I'm more than welcome to answer them. I will even provide my mail in the chat so we can talk about this some more. Thank you.